Welcome back, everybody. Today's lecture is Compilation, Gate Scheduling, and Parallelism, and I am Jonathan Baker. In this lecture, we're going to introduce several concepts related to the compilation of quantum programs, specifically transforming input programs into ones that can be executed directly on hardware. At a high level, compilation, as we've seen, is a function on whole programs, transforming some input program to another equivalent output program, however, with some modifications. We saw earlier one example of this, converting the gates of the input program from one gate set to another. Why might we do this? For example, the target hardware does not support certain types of gates that we use to write the original program, and so this compilation step is actually one that's necessary. Other compilation steps, however, are not required, but serve as optimizations, transformations to make the program more efficient. For example, by reducing the total number of gates needed to express a quantum program, or reducing the amount of time it takes the program to run. Here we've highlighted where scheduling falls into the grand scheme of compilation. This is just one small part of a much more complex system. In this lecture, we're going to explore some of the fundamental objects used in the compilation of quantum programs, namely dependency graphs, and then explore how to use these to solve one piece of the whole compilation problem, which is scheduling gates. This problem is intimately related to many other compilation problems we will explore in future lectures, like mapping and routing. For now, we will assume these problems have been solved for us, and so stay tuned for future lectures. So far, we've seen many examples of quantum programs, and just as a short refresh, these programs are represented by these quantum circuits, where each line is a qubit and operations occur on one or more of these lines. Time flows from left to right, so gates occurring on the same line are ordered. For compilation, we want a more practical representation of the input program to better understand the dependencies between gates and qubits in our program. We will use the so-called dependency graph, a graph representation of the whole input circuit. Let's quickly recall a graph's data structure. A graph G is this pair V and E, a set of vertices and edges. Where in a simple undirected graph, the edges are sets with two vertices. Here E of G has, for example, A, B, indicating there's an edge between vertex A and vertex B. In a directed graph, however, the edges are ordered pairs, UV, where the edge begins at U and ends at V. For gate scheduling, we care about the dependency graph, which is a directed graph, as is seen here. And in particular, it's a directed acyclic graph, or DAG, a directed graph which does not contain any cycles. The edges in this graph are, of course, ordered, so we've seen an adjustment to E of G. So instead of having A and B in any order we want, we now have B goes to A because it's now directed in this graph. Let's take an example from before and construct its corresponding dependency graph. Rather than working with the whole program, so here I've taken a piece of that adder. Let's assume that all the gates have been decomposed for us. So for example, this Toffoli gate in the top left on Cn, A0, and B0 has been decomposed into its 6 C0 decomposition. And also because it's a lot of gates for this presentation, we'll just truncate it to the first several gates. Okay. As a convention, which is useful for tracking the start of the program, we start with a single node. Here we've labeled it with -1, an empty operation, but we will imagine as operating on every qubit. We have this auxiliary data structure, which is keeping track of which vertex used which qubit last. So for example, we're imagining that -1 operated on all the qubits. So we've updated our table so that Cn, A0, et cetera, are all marked with -1, the node. Then beginning from the left, we scan the circuit for the first operation on any qubits. We don't care which one happens first. We insert a node into our graph labeled with this operation. So here we'll just imagine that op0 corresponds to the first C0 between B0 and A0. Of course, this C0 is ordered. We want to know which one is the control and which one is the target. So we'll make note of that as well. We can then check our table for every qubit which is used in this operation and draw an edge from the nodes that it's marked by to this new node. So here A0 and B0 were both used by -1. So we write an edge between that node and op0. If, say, it used different nodes, we'd have multiple edges coming into this node. Finally, we update our table with this new node. The operation uses only 2 of the many qubits, so we only update those 2 rows. So we see here we've highlighted A0 is now last used by op0 and B0 is last used by op0 as well. We then continue through the circuit until all the operations are done. Here we add in the next C0 between B0 and Cin, which is highlighted in the top left. And this depends on both op0 and -1, because in our table from before, we see that Cin was last used by -1 and B0 was last used by op0. And of course, we update the table accordingly as well. So Cin is updated and B0 is updated. We keep doing this for all the operations in the circuit. Here is the last step where we add in the final node to mark the end of the circuit. And here we've marked it with infinity. It's a do nothing node, just to mark the end, to know we're done scheduling. The table is indicating the step right before this last edges have been added in. The circuit diagram essentially encodes all this same information that we have in the dependency graph. We could have figured that we have choices in which thing to order first. But we're not usually given a circuit as our input. We're instead given some text file that contains, a long list of instructions, say in the CHASM language. And that list of instructions doesn't have any order, obviously, inside of it. And instead, we want to convert that list file, that giant list of instructions, into a graph that we can work with. So rather when I say scan from left to right, it really means read the instructions in one by one. And those are in the order of the program. So we can adjust, we can write our dependency graph to capture the relations between gates in that file. One important question we might ask about a given circuit is how long will it take to run? The simplest way to consider this is to look at the critical path of the input circuit. This is the same as finding the longest path from start to finish in the corresponding dependency graph. In fact, our start indicated by this -1 and end ended by inf. While computing the longest path between nodes in an arbitrary graph is hard, luckily finding it in a DAG is easy. First, we put the graph into topological order, which we've done here. Then for each node in order, we look at the incoming edges and the weight of the nodes themselves. Whichever sum is largest, we assign to be the weight of the new node. In this program, it's fairly easy to see the critical path by looking at the qubit B0 in the original circuit and noticing all but one of the gates uses B0. In fact, we have to go to this line to execute many of these gates. If all of the edges are weighted 1, then the length of the critical path will be 9. Quantum gates, however, are not the same duration. For example, single qubit gates tend to be much shorter than 2 qubit gates. To account for this in computing the duration of the program, we can weight the outgoing edges of each operation as the duration of the gate. For example, if 2 qubit gates are 2 units long and single qubit gates are 1 unit long, then we can update our previous graph with these weights. And then we can recompute the critical path of the circuit. Some connections in the dependency graph are redundant. We can simplify our previous dependency graph, which may make the compilation process easier, by considering the transitive reduction of this graph. That is, we want to produce a new graph which captures only the necessary dependencies and remove this redundancy. We need to make sure that if there is a path from A to B in the original graph, then there will be a path to A to B in the final graph. For example, we notice that op3 depends on op0 and op2, but op2 already depends on op0 being completed, so this arrow between op0 and op3 is redundant. So we see that the path op0, op1, op2. So op2 depends on op1 being done, which depends on op0. So we don't need to write a dependency between op0 and op3. What we're doing is maintaining the same reachability between nodes. We can always reach the same nodes from each other in the final graph. There are many more instances of this edge, these edges which can be removed, and we've done here. So we've marked each of the edges that are redundant with an X. The transitive reduction of this particular program segment makes the critical path much more obvious after removing all of the marked edges. It is also relevant for scheduling gates, as we'll see in a moment. So far, we've looked at the dependency graph representation of input quantum programs. And we've assumed that the order gates appear in the input program are the order the gates will need to be executed. So for example, I wrote my algorithm in one way, and I decided I need to do operation A, then B, and C. But it may be the case that that order isn't necessarily the way I need to do that program. Some, but not all operators commute. Two operators A and B commute. That is, the sequence AB is equal to the sequence BA if they commute. And we can check if any two operators commute by computing their so-called commutator, which is defined below as AB minus BA. And if this is equal to 0, then we know that we can switch the order of A and B essentially for free. This will give us more choice when scheduling gates. Let's take a look back at the original circuit. There are a few places we can take advantage of the fact that certain pairs of gates commute. For example, the C0 between A1 and B1 at the bottom commute with all of the other gates in the circuit because they don't share any qubits. We can show this by the purple arrows spanning the whole range of the circuit. And we can slide that C0 into any position along the way. Second, the first two C0s is between B0 and A0 and B0 and Cin also commute. You should verify that this is true. The quick trick is to see that they're both just controls on the same qubit, and they target different qubits, so those can switch. So what we've done here is identify mutually commuting sets of gates, and we can use this to update our dependency graph prior to the transitive reduction. So to update, we first remove dependencies between gates in the same commuting set. So this would be op0 and op1, which we've identified with an X. We then derive new dependencies between the commuting sets. In this example, we now must add an edge between op0 and op2 to indicate that both op0 and op1 must be completed before op3 can be executed. However, this now gives us a choice between choosing op0 and op1 when choosing which to execute first, which is exactly what we wanted to accomplish. The commutation rules of gates on different qubits are implicitly accounted for in the way we've constructed the graph originally. So for example, this bottom C0 between A1 and B1 was allowed to move at any position along the way. This was already captured because it didn't share qubits. So we see that op4 here, which corresponds to that C0, can be executed early or later because it doesn't occur in this chain below. In currently available NISQ machines, qubits have limited lifetimes due to decoherence or the loss of state. The primary objective of a scheduler is to maximize the utilization of qubits within their lifetimes, meaning the first time they are used to when they are measured at the end of the circuit. As a practical objective, schedulers attempt to minimize the total circuit depth, that is, the duration of the longest critical path in the circuit. Given an input circuit, the expected qubit lifetimes, and the duration of gates on those qubits, we're able to predict if the circuit is generally safe from qubit idling noise, this decoherence. This objective is simple to optimize for once a program has been passed to the scheduler. That is, all qubits have been mapped and extra commutation or communication has been added. However, it does not tell the whole picture. Continuing with our example before, suppose the whole circuit can occur in 100 units of time, but the lifetime of A1 is only 90 units. This measure would suggest the circuit is not very safe to run because we might execute this gate, the C0 on A1 right away. However, if we simply delayed it, we would be okay. So say we did it at the end or closer to the end of point 2. It won't use all of its lifetime of 90. A different way to characterize programs is by their space-time volume, which accounts for how long qubits are actively being used. So if they haven't been used at all during the circuit, we can say they're not being used at all, they haven't been initialized, and they only begin active use once the first gate is executed on them. That is, we want to know if it's possibly in some state other than the ground state. And in this case, it might be, depending on where the circuit falls into the larger quantum program. In our example above, the C0 is executed if it's executed right away, its space-time will be 100 units. But if we put it, so for example, at position 1, but if we put it somewhere closer to position 2, then its space-time will be less than 100, and we'd be more safe to run that circuit because it'll be subject to less idling noise and less probability of it falling out of its state. This also is not the whole story. So a quantum system is subject to a wide variety of other noise. Another prevalent source of noise is crosstalk, usually occurring when multiple gates are executed on nearby qubits. So for example, we've highlighted these two C-naughts which occur in the original circuit in parallel. And these might be hard to do with high success rate if they're executed right in parallel. When scheduling these two gates, we may actually want to intentionally delay one to avoid this crosstalk error. In this circuit, it's convenient that we can simply shift the bottom C-naught to whichever position we want. But in general, these delays can result in larger per qubit space-time volume. So there is some balance that we need to do to make sure we don't spend too much extra time making sure we don't have crosstalk, so that so the circuit still runs quickly, so we don't incur other loss to decoherence, but also not too much loss to crosstalk. So there's a balance between these two things in scheduling objectives. Scheduling, we're going to talk now about a few scheduling strategies, some very simple ones. Scheduling can be done at the logical or physical level. So for example, in fault tolerance, we're scheduling logical qubits, but in the near term, we're scheduling physical qubits. For current machines, this means that we schedule the circuits basically as is, since each gate in the circuit corresponds to a single gate in hardware, possibly more depending on a decomposition. In the case of error correction, however, the fault-tolerant regime, we may perform some multi-level scheduling strategy by scheduling the logical operations, the ones that compose many physical qubits, one way, and then scheduling the physical operations another way. We're not going to cover that in depth here. The first simple scheduling strategy is the as soon as possible scheduling, ASAP. This strategy is very simple. From the constructed dependency graph, we start by looking at the -1 node, the start of our circuit, and build a frontier of possible operations to perform by looking at all nodes connected to it. Here we consider blue to be the completed operations, those which have been scheduled already, and red to be those in the frontier, i.e. operations that we have a choice to perform next. So here we have 3 choices. This, of course, is using the commutation relaxed dependency graph. In the first step, the -1 node is considered completed because it doesn't actually do anything. And the next 3 operations are red in the frontier. The schedule has 3 options to choose from as the next operation to execute, or multiple if they can be performed in parallel. So for example, if we could do 2 C-naughts at the same time, we can just go ahead and execute or schedule both of those. But one choice will not impact the other. We could choose the first one in that parallel operation, and then the subsequent step could then choose to do another one because it doesn't interfere. Suppose we choose the middle operation, and then all adjacent nodes are added to the frontier. If all of their incoming nodes have been completed. Here, for example, we cannot add this purple node because we haven't yet completed the red node down below, and it depends on both of those things. So purple is not added to the frontier. Instead, we're left with only a smaller frontier containing the 2 red nodes. If the bottom operation is then selected, then we can add this next gate to our frontier. And the ASAP algorithms proceed until all of the gates have been scheduled. When the scheduler has multiple choices, so for example, we had 3 choices at the very beginning, different heuristics can be used to choose. For example, we may prefer to choose operations along the critical path so that we can sort of guarantee that that path will be executed quickly, which is going to be the longest path in our circuit anyway. A very similar strategy is to execute as late as possible, ALAP. This simple strategy starts with the end of the circuit, so with that inf node at the end, marked in blue, and schedules the last gate needed to be completed, and goes backwards from the previous gates. So why might we choose ASAP versus ALAP? The primary benefit of this as late as possible strategy is when qubits have limited lifetimes, and therefore it is beneficial to initialize them as late as possible. So we don't want to start, so for example, we saw at the beginning or earlier that C-naught, if we executed it early, would incur a larger space-time cost. This strategy will attempt to avoid that by initializing qubit gate or by executing gates on uninitialized qubits as late as possible, minimizing that space-time volume. These are two of the most basic strategies and often effective without needing to account for more of the complex factors like crosstalk, etc. There are many more complex strategies, and we'll review them very briefly. The first is an optimal solution. What does an optimal solution mean for scheduling? It depends on the specific objective. In cases where the input program has been fully mapped and routed, the objective is simple, that is minimizing execution time. The problem, as we saw, was easy for the ASAP and ALAP algorithms, and that's sufficient. In other situations, this isn't the case, specifically with more complex objectives, which attempt to account for many more device-specific parameters like crosstalk error. Next is communication-aware scheduling. When communication operations have not been directly added into the circuit, the scheduler may want to take into account costs of communication. 2-qubit gates between qubits which are distant will require much more time to execute because of extra communication operations. These costs are, of course, architecture dependent, and a good scheduler will account for these costs. One strategy involves the insertion of barriers around high communication operation or high communication costs 2-qubit gates, and we'll cover this more carefully in future lectures. Finally is adaptive scheduling, where the scheduler not only decides the order of the gates to occur, or decides, and when to execute them, but choose the specific implementation of the desired operation. For example, in the case where a qubit has 2 or more implementations based on the specific target hardware, it may choose the best based on gate time, gate qubit fidelity, or qubit noise. This strategy is highly dependent on knowing details of the device in order to make good decisions. Okay, let's just do a quick recap. So today we've covered several important concepts related to program scheduling. First, we covered representations of input programs, converting input programs into something more workable in the form of dependency graphs. Next, we covered manipulations of this representation to simplify the graph for scheduling, and how to account for commutativity to give the scheduler more options in which gates to choose. Finally, we covered some simple scheduling strategies in detail and others at a very high level. In the next lecture, we'll cover more of this.